So today I have the opportunity to give you a brief overview of this unique collaboration between the National Energy Technology Laboratory and Cerebras Systems. But first, I do want to acknowledge my collaborators. It's from NETL, we have Mina Wu and Terry Jordan, and myself, Dirk Van Essendelft. And from Cerebras, we've been working most closely with Michael and Jeff and Mark Hare on a very regular basis, and a smattering of other people mixed in throughout the needs as they come along. So we really appreciate that. It's been one of the best collaborations I've ever been a part of, to be quite frank. And first, I want to tell you a little bit about the National Energy Technology Laboratory, because I'm sure many of you have never heard of this. We go by NETL for short, and NETL is one of the 17 national labs in the Department of Energy. NETL falls underneath the Office of Fossil Energy and Carbon Management, and our mission is to develop and promote new fossil energy and/or carbon management technologies to help meet our nation's energy needs in a carbon neutral way. While the nation has made substantial investments in renewable energy technology, fossil energy will continue to be a substantial portion of the nation's energy portfolio as economics, stability, security, infrastructure, and energy density make it impractical or impossible in some cases to completely replace fossil energy resources with alternatives. With this fact in mind, the Department of Energy has been investing in scientific modeling and artificial intelligence capabilities to develop and support novel carbon neutral fossil energy technologies. With this collaboration is part of that investment between NETL and Cerebras, and we're planning to dramatically accelerate scientific modeling. Just a little bit background on where we're headed as a nation within the Department of Energy and Fossil Energy. The Department of Energy has recently announced the Energy Earthshots initiatives, which you can find at that link at the bottom left corner of the screen. And it's a collection of strategic initiatives to advance scientific and engineering technologies to decarbonize the electric grid by 2035 and the entire economy by 2050. Some specific activities that NETL has been involved in to support these initiatives include the design and development of novel energy efficient fuel conversion technologies, carbon capture from point sources, new direct air capture technologies, geologic CO2 storage, and hydrogen generation from fossil sources with carbon capture that's becoming known as blue hydrogen. The 2035 and 2050 goals are quite ambitious and require extremely fast development cycles to get to the real systems deployed in that time frame. In order to support these efforts, NETL is investing in wafer scale technologies like yours to dramatically accelerate modeling of fossil energy and carbon management and carbon capture and storage devices and systems. The faster we can model these systems, the faster the design cycles can be. Further, if we model these systems at or faster than real time, we can use this technology as digital twins to help improve security, reliability, and flexibility. But all of this modeling and the cornerstone of this type of technology falls into a class of modeling known as field equation modeling. Field equations are fundamental to virtually all science and engineering and are used to describe the physics of fluid flow, electrostatics, magnetism, gravity, waves, and much, much more. Physical fields have two important properties. First, they have a value everywhere in space-time. The value only changes in response to local changes to the immediate surroundings, and this is known as the principle of locality. These properties give rise to characteristic partial differential equations that describe the physical phenomena that surround all of us. On a computer, we approximate these equations through discretizations, where we break physical space up into a grid of cells and approximate the continuous field as pointwise distributions in that cell. And we approximate the derivatives of the characteristic differential equations by difference models. So what we've adopted in the Wafer-Scale Engine is this very simple mapping of the discretized space into the onto the wafer, where each processor holds a column of Z cells in memory, and the other axes are distributed along the fabric. The Wafer-Scale Engine is so good at modeling field equations because the principle of locality and discretization. The way that we do our discretizations is reflected in the hardware design. The heart of field equation modeling is recognition that the derivative terms are approximated through my own local cellular value and that of my immediate neighbors. Thus, any system that is designed with processors that can minimize access time to my own data and that of my neighbors is going to excel at this kind of modeling. The Wafer-Scale Engine gets its speed because of the incredible memory bandwidth across the router and router bandwidth and the single cycle latencies. Every tile on the Wafer-Scale Engine can access its own local memory and that of its neighbor in roughly one cycle. Further, the read-write bandwidths are balanced such that the operations can be completed in half to single cycle rates in single precision. Current generation distributed computers are very imbalanced in computing horsepower relative to memory and network bandwidth and latencies. These imbalances create significant choking points in scaling that we'll soon see in this talk. The Wafer-Scale Engine, on the other hand, has an ideal balance of latencies, bandwidth, and computing power, which enables scaling down to very small workloads per processor. While this is a fantastic achievement in computing, practitioners need a very simple method to program and solve equations. This is where the NETL and Cerebras collaboration comes into play. NETL and Cerebras have been developing a domain-specific language to solve field equations. We are calling it the Wafer-Scale Engine Field Equation Application Programming Interface, or WSE-FE API for short. So it's a hybrid code between Python and Angular. It has a very simple NumPy-like interface that allows users to program the WSE in just a few simple lines of code. So what we're going to do to kind of walk through this is just to consider a simple field equation that describes the temperature distribution inside a solid block. Here we initialize the block to a temperature of 500 Kelvin, and 4 of the sides are held at 500 Kelvin, and 2 of the sides are set at 400 and 300 respectively. And the system is then allowed to evolve in time. And actually, the entire program to solve this explicitly is shown on the left-hand pane here. And so, I don't know, we have like 15 or 20 lines of code to solve this and get this running up on the Wafer-Scale Engine. Completely done in that. And so, using the explicit method, the update rule for temperature looks like a stencil with off diagonals and the center having separate but related coefficients. This is identical to a 3D convolution in machine learning. This is programmed in the Wafer-Scale Engine, as I mentioned, in just a few lines of code. And when we compare the solution to an analytic solution and to our own validation code, they match almost exactly to within about 0.15% error, which is quite good. Not only do we get the correct answer, but the time to solution is absolutely incredible. We compared our API on a single Wafer-Scale Engine to a 10,000 core CPU allocation on Joule, our Joule 2 supercomputer here at NETL, using one of the most advanced CFD software packages in the world, known as OpenFOAM. From this plot, it's clear that the scaling for OpenFOAM stops at about 3,000 time steps per second, which is over 10 times slower than the Wafer-Scale Engine at maximum memory capacity. Further, the Wafer-Scale Engine scales very well over several orders of magnitude problem size. and can achieve over 830 times actually, faster speeds than OpenFOAM on Joule 2.0. And for the 10,000 core allocation that we were able to get on Joule, the Wafer-Scale Engine was a minimum of 42 times faster than the distributed computing approach, and should always be about 10 times faster, regardless of how large the allocation is for this particular problem. We found that the scaling was only influenced by the number of cells in the memory axis, which is not surprising given how we have architected our software. With a few minor changes, the code, the problem can be solved implicitly. This is typical for most CFD codes, which have small cell sizes, as it can allow for larger time steps to be taken. Again, we compared it to the OpenFOAM on Joule 2.0 with 10,000 core allocation. And here we see a different performance window for the Wafer-Scale Engine, which reflects the presence of the two global reductions in the solver iteration. The Wafer-Scale Engine has a major advantage here because the reduction can be done in about the same time frame as it takes to do as the minimum latency between two distributed nodes. In comparison, a 10,000 core allocation to Joule, the Wafer-Scale Engine was about 200 times faster or more than OpenFOAM, which is truly impressive. This is a massive leap in performance that the nation needs, really. So how do we make this work? Well, we make use of Python's magic functions to decompose operations into a set of order of operations correct sequences within a singleton class in Python. The bytecode controlled sequence and arguments vector gets optimized and compiled into a binary along with the Angler code and initial conditions. The binary gets run on the Wafer-Scale Engine allocation, which consists of a control tile and a set of workers and motes, which I'll show you shortly. The controller's job is to interpret the bytecode and send control wavelets to the workers and mote tiles. The workers and motes receive the control wavelets and activate tasks, which together complete unary, binary, and ternary operations defined in the original Python API. So here you can see the layout of the controller in orange and a set of broadcast tiles in yellow, motes in green, and workers in blue. The control tile sends out control wavelets along the black lines for the workers and motes to complete. Reductions then follow a similar path back to the control tile. And we should note that we're also working on what would be needed to place the control tile in the center to improve the reduction speeds and latencies. We currently compile the program sequence and arguments into a binary along with the initial boundary conditions. However, there is no reason that we could not that this could not be streamed across a network. In addition, we could also use the memory space in the rebroadcast cells to expand the program space available to the Wafer-Scale Engine should we need it. The slicing of WSE array objects is similar to NumPy, but is always in relative terms to the position in memory and the tile's position. The first axis slice specifies which cells in the memory axis to apply an operation to, while the second and third axis define the position relative to the owner of the data. The second axis indicates the east-west direction, while the third axis indicates the north-south direction on the wafer. A 1 in these positions indicates east-north, and a -1 then indicates south and west. Setting both positions to 0 means that I'm working with my own data, not my neighbor's. The Python magic functions are used to assemble a preliminary control sequence and an arguments vector sequence into a sequence that's held in the singleton class and managed there. The control vector and sequences consist of arguments, usually an arguments load and a binary, unary, or ternary operation command. In this case, the 5 is a binary subtract from center operation. The preceding 0 tells the worker and motes to load the set of arguments and that specify the source 0, source 1, and destination addressing, as well as the vector length. The last two integers are optional and interpretable constants for various different kinds of operations. The controller has three main tasks to send control wavelets and arguments in the right order to run the program as written, to coordinate global reductions and math with global scalars, and to handle the control flow that's necessary with loops and conditionals. The controller tile on the Wafer-Scale Engine dynamically interprets the bytecode sequence at runtime, and we have written it to be efficient and hide the interpretation latency as long as the memory access is greater than about 16, and we can probably do better than that if we spend some time optimizing this. This allows the program to be flexible without need for host Wafer-Scale Engine interaction. It also allows us to do looping with conditional exits, as you can kind of see here demonstrated in this sample bytecode sequence. And these kind of operations are absolutely necessary for complex CFD. And so I think we have all of the pieces and bits and bobs together to do full-fledged CFD. And finally, we get to what actually gets run on the Wafer-Scale Engine. This is where the Angular code comes in. And so here we see operations for the workers and mote tiles. And this is an example of a neighbor multiply binary operation. The worker code is relatively simple. It sets addresses and lengths off of pre-read arguments, launches a microthread to send the source 0 data to its neighbor, followed by launching a separate microthread to do a fused multiply with the S0 and S1 address space, and store it in the destination address space. The mote code is similar, but either does not participate, or does just the send portion or just the receive portion, depending on the communication direction. We have, I think, all of the basic functionality of the API up and running, and it appears to be stable. We now are working on expanding the complexity of the models we run. The next problem we are tackling is scalar transport in a fixed velocity field. As a test problem, we're solving the temperature field in a fluid moving across the hot plate. This is a good candidate problem because it involves a slightly more complex AB formation than the diffusion. It has non-symmetric matrices and associated solvers with it. It has nonlinear updates that we have to manage as outlets have to be updated with the from the fluid field. Further, it's a well-studied problem, and we have plenty of examples for validation. We are currently have the formation of the non-symmetric solve working, and I just got the nonlinear update working just this past week. And so we should be, I have this working basically in simulator, have a little bit of polishing to do, and then we'll start trying to run this on actual hardware and validate the results that we get against known solutions. From there, we're going to be solving the full Navier-Stokes with the simple method. We're going to be doing this with a demo of what we call lid-driven cavity flow. This is the kind of flow that in circulation that's set up when wind blows across a lake. You can think of the wind dragging the surface of the water across, and it sets up these recirculation currents inside of this. This is another very well-characterized CFD problem that almost every CFD code goes through validation against, and so we're not going to take any deviation from that path. From there, we'll start building out capability for non-uniform grids, non-rectangular geometries. We can also include turbulence models, chemical reactions, and this will form a really quite comprehensive first-generation CFD capability on the Wafer-Scale Engine. And we expect to be in the multiple hundreds of times faster than what is possible on current generation hardware. Truly phenomenal project. I really have loved being a part of this, and have really enjoyed working with your team And I very much appreciate the opportunity to speak here today. And with that, I think we'll just conclude and try and take some questions.